Once again, I'm Sean Radley, Senior Consulting Engineer with Simpson, Gumpertz, and Heger. I work out of their Boston office. And today I'll be discussing a TechNote that ACI 364 recently republished titled Increasing Shear Capacity Within Existing Reinforced Concrete Structures. We'll open up the session discussing the scope of the TechNote, followed by a brief discussion of structural strengthening in general. But the main focus of the presentation will be the various methods of shear strengthening described in the TechNote, specifically section enlargement, internal reinforcement, external reinforcement, near surface mounted reinforcement, external post-tensioning, FRP composite systems, and FRCM systems. And then we'll close with some considerations for selecting a suitable method. The TechNote opens up with one main question: what options are available to increase the shear capacity of members within existing reinforced concrete structures? And within the TechNote, we reference various ACI codes, guidelines, ICRI guidelines, and author documents in order to answer that question. And I present those references throughout the presentation here and also in summary at the end. Structural strengthening may be needed due to various reasons. Perhaps you have higher loads on your existing structure due to either change in use, additional equipment, perhaps high density storage as an example, or if you're on a plaza, maybe there are additional planters. It could be due to deterioration. As Fred noted, there may be corrosion of embedded steel reinforcement causing concrete deterioration and subsequent section loss, or possibly due to damage by impact, overloading, or fire. There may be deficient design. Perhaps the older detailing requirements required by previous codes no longer are applicable in your project's case. Or there may be construction errors, missing reinforcement, or misplaced reinforcement. Whatever the reason and whatever the method selected, it's always recommended to perform an engineering analysis and design by a licensed design professional familiar with the selected technique. Now we'll get into the main focus of the presentation, which are describing the methods of shear strengthening. We'll lead off with section enlargement. In this method, the existing concrete structure, whether it's a beam, a joist, column, or wall, the shear capacity is increased by enlarging the section. You can see in the photo on the left, we've got a section enlargement of a joist. Now, the section can be enlarged either by concrete or a specialty repair mortar. In that photo, we've essentially increased the width and the depth of that particular joist. In the photo on the right, we're increasing the shear capacity of the slab above for punch and shear by constructing a shear collar at the top of the column. For each of the methods that we'll talk about today, we present a similar format where we discuss the considerations, followed by advantages, and then disadvantages, and then also some locations where you can go to for further reference or further guidelines. So for section enlargement, what do you need to consider? The first is that it's a passive method, meaning that unless the existing structure is shored and unloaded by, say, hydraulic jacking, once the strengthening technique is employed, it's only going to be engaged and strengthened for future additional loads. It won't be able to undertake existing loads. Another consideration is that, as Fred noted again, you want to repair any deteriorated concrete at the surface where you're enlarging the section. Similarly, you want to prepare the surface of the existing concrete where it abuts the section enlargement. And within that section enlargement, you also want to consider what supplemental reinforcement will be installed. It can be somewhat of a balancing act where you may have diminishing returns. In other words, on one hand, you're increasing the section, so you're increasing your capacity. But on the other hand, at the same time, you're increasing the dead load and the demand. In the case of section enlargement for repetitive members like beams or joists, you want to think about how the added stiffness may also alter load distribution in the existing structure at areas away from the section enlargement. Some advantages: this technique uses conventional construction methods and is economical. However, as noted, we have to deal with added weight and also loss of headroom and space. And you can see this in the figure below, where we've got a shear collar at the underside of a slab, where we need to think about how that shear collar may or may not affect the headroom or the area around the column. Further guidelines are provided in ACI 546 and ICRI 330.1. The next method is internal reinforcement. In this method, new reinforcement is drilled and bonded within the interior of an existing concrete member. The reinforcement can be smooth or deformed, and the bonding technique could either be cementitious grout or an epoxy adhesive. The goal of this method is to cross potential shear cracks. Again, this is a passive method, and because we're now drilling into the interior concealed surface of an existing member, you want to use non-destructive testing to avoid cutting, damaging, or drilling through existing reinforcement and possibly some embedded electrical conduits. It's a relatively easy method, uses commonly available equipment. However, it can be difficult to develop the reinforcement. You can imagine over a very short length, to get that reinforcement developed, you may need to use headed bars or threaded rods with mechanical nuts at one end, as shown in this detail below. If you've got a lot of reinforcement within the existing member, it may also be difficult to employ this technique. Because you actually need to physically get adjacent to the member to install the additional reinforcement using a drill, you also need to have space around the member just to install it. Further guidelines are provided in ACI 546. The next method is external reinforcement. As opposed to the previous method, where we were installing reinforcement within the concrete member, external reinforcement installs supplemental members on the exterior surface of the member. It can be plates, channels, angles, or similar members. It also can be steel or FRP. And the supplemental members can either be mechanically fastened, either through through bolts or partial depth fasteners, or they can be bonded using epoxy adhesive. In the image on the left, you can see a new steel plate, a new series of steel plates installed at the web of a beam that are through bolted to the beam. And in the image on the right, you can see some similar CFRP strips. Again, this is a passive method. If mechanical fastening is employed, you need to consider edge distance and group action of the bolts. Surface preparation and composite behavior are also important considerations. Since we now have exposed elements, in the case of steel, if that material is selected, corrosion protection should be considered. In either case, whether it's steel or FRP, fire protection may also be a consideration that needs to be included. Moisture diffusion. It may be more beneficial to utilize intermittent strips of supplemental members rather than enveloping the entire member in a large plate or U-shaped plate, just to allow any trapped moisture or future moisture to have a way of getting out. This method is useful where space constraints adjacent to the existing structure may limit the use of the previous method, internal reinforcement. If FRP members are selected, that's advantageous in that they have a high strength to weight ratio. Disadvantages. This method shares a disadvantage that all similar external methods have, in that the existing structure needs to have a minimum unrepaired strength, meaning that if the external reinforcement is damaged and can no longer be relied upon, the existing structure will remain standing and will not collapse. If steel is selected as the material, it may be difficult to install due to its weight, and it may be expensive. Now, however, that depends on the extent of the supplemental members. If epoxy is chosen as the bonding technique, potential degradation over time may also need to be considered. And lastly, as with all external methods, aesthetics needs to be discussed with the owner and the architect because we're now changing the final look of the exposed structure. Further guidelines are provided in ACI 440.2, 546, and ICRI 330.1. The next method is near surface mounted reinforcement. As shown in the photo on the left, this method entails saw cutting narrow, shallow grooves in the surface of the concrete, after which is performed, the grooves are cleaned out, and then new reinforcement, whether FRP bars or can be mild reinforcement as well, is inserted into the groove and then bonded to the existing concrete member using either a cementitious grout or an epoxy adhesive. You can see in the detail on the right the method employed. However, this, I'll note, is actually for a flexural strengthening of the top side of a slab, but you can imagine that the method employed here is applicable to shear strengthening of a beam web per se. You can see our narrow saw cut, only 1.25 inches wide, and it's very shallow, 2.25 inches deep. That's by design. You don't want to be saw cutting through all of the existing reinforcement at the surface of your member. The new reinforcement is embedded within the saw cut chase and then bonded to the existing structure using, in this case, cementitious grout. Again, this is a passive method. Our understanding is that it's not typically used for shear strengthening, typically more so for flexural strengthening, although it does have applications in the shear strengthening world. As previously noted, you want to figure out and understand what the depth of the concrete cover is in your structure so that when you're saw cutting all these chases, you're not actually damaging and saw cutting through the existing reinforcement. Additional considerations are corrosion protection for the new supplemental reinforcement, as well as its development. Because we presumably know where the existing reinforcement is, we have a reduced chance of damaging existing reinforcement, as opposed to, say, previous methods where we'd be drilling into the interior surface of the member. Disadvantages: it can be difficult to develop the bar, and as noted, there may be some limited applications for shear strengthening. Nevertheless, it's an available approach. Further guidelines are provided in ACI 440.2 and ICRI 330.1. The next method is external post-tensioning. As shown in the image on the left, this method involves mounting post-tensioning tendons on the exterior surface of an existing concrete member, anchored at various locations, consisting of the dead end, intermittent locations along the length of the member, and then the live end. And from the live end, the supplemental post-tensioning tendons are pulled or tensioned and stressed in order to offset internal stresses due to existing or future surface loads. You can see in the image on the right, the photo on the right, an example of external post-tensioning of double T-beams. This is our first active method. The previous methods have all been passive methods. This method instantaneously engages the entire structure and is beneficial in that it can support both existing loads, such as dead load, and also additional long-term loads, such as live load or any future superimposed loads. My understanding is that it's primarily used for flexure. However, there are some secondary benefits that can be reaped by shear strengthening. Because we have exposed tendons on the exterior surface of our structure, we've got to think about corrosion and fire protection, as we did with the previous external technique. It's a balance of strength and serviceability. So we, of course, need to design for the strength that we need, but we also need to be conscious of any immediate and long-term deformations, deflections, and rotations, particularly how it affects adjacent construction. And we're dealing with significant internal forces, and associated with that, we've got to design and make sure the existing structure is capable of taking the bursting stresses at the anchorage locations. Another consideration for the design is long-term and short-term post-tensioning losses. One main advantage of this technique is that it provides greater strength increases than the previous passive methods, and it also closes any existing cracks you may have. However, as noted with the previous external method, the existing structure needs to have a minimum unrepaired strength. Should these tendons be damaged and no longer able to be relied upon, the existing structure cannot collapse. It needs to have enough strength to support itself and service loads. Because of the extensive nature of this approach, it may be difficult to install in congested interior locations and require specialty contractors. As noted before, aesthetics also need to be discussed and agreed upon prior to selecting this method. Further guidelines are provided in ACI 546. The next method is fiber reinforced polymer composite systems, or FRP systems. In this method, high strength carbon fibers are embedded in a structural grade epoxy resin and mounted or bonded to the existing structure to increase the shear capacity. The main function of the fibers is to act as the main reinforcement for the composite system. It's the tensile reinforcement. And the main function of the epoxy resin is to both protect the fibers, to bind them together, and also transmit the forces from the existing structure into the fibers and also between the fibers. You can see in the photo on the left an installation of an FRP composite system installed on a spandrel beam. You'll also note in this photo there's some elements of an external post-tensioning system installed at a column. In the photo on the right is an installation of an FRP composite system installed on a shear wall. This, again, is a passive method, and it's also a bond-critical application, meaning that the shear stresses between the existing structure and this strengthening technique are transferred at the interface between the existing structure and the composite system through bond alone, with no reliance on mechanical fasteners or interaction. And so surface preparation and repair of deteriorated concrete at the surface are critical. It's a high strength, lightweight system, and as opposed to the previous FRP methods, which we discussed, including plates or strips, which were inflexible, this is a much more flexible approach and can conform to various geometries. And as such, it's easily installed and also is non-corrosive and can be cost-effective. However, as we previously noted, for similar external techniques, the existing structure needs to have a minimum unrepaired strength. In addition, the applications on moist surfaces at high humidity and low temperatures may be limited. If you're completely wrapping an existing structure or even three-sided U-wrapping it, you may need to think about moisture diffusion, as we previously discussed, because this method, our understanding is that it acts as a vapor barrier. Again, aesthetics needs to be considered, and this method requires trained contractors to install. Further guidelines are provided in ACI 440.2 and ICRI 330.1. The final method is fabric reinforced cementitious matrix systems, or FRCM systems. In concept, this method is similar to FRP composite systems, with one main difference being epoxy resin is not used here. Instead, cementitious matrix is. You can see in the photo on the left, the installation of FRCM on a wall, and in the photo on the right, installation of the underside of an arch. It shares the same considerations as we discussed for FRP, namely its passive method, bond critical, and surface preparation and repair of deteriorated concrete are critical. It offers better performance under elevated temperature, humidity, and UV than FRP composite systems. It's also non-combustible and easily installed. However, it's a relatively new material, and my understanding is that it's not frequently installed by contractors, and while ongoing, the results of durability testing are limited. Further guidelines are provided in ACI 549.4. So now we'll discuss briefly some considerations in method selection. It's a balancing act of many different variables. The first is, what is the cause for strengthening? And this should be a direct result from your condition assessment, which is one of the main goals of any condition assessment. What is the magnitude of strength increase required? Certain methods offer greater strength increases than others. Do you need to support future loads only, or existing and future loads. That may dictate which type of method, passive or active, you choose to select. The size of the project may come into play as well. For example, if you have a very small project, it may not be warranted to use an extensive method such as external post-tension. Cost and schedule always are a consideration. Environmental conditions may decide which method you select. For example, if you have high temperatures or low temperatures or a very moist environment, it may not be warranted to use FRP or FRCM. In addition, indoor air quality. If you're within a parking garage or an occupied building where you have to coordinate around existing building tenants, odors and dust need to be thought through. The strength of the existing concrete substrate, particularly for methods that are bonded directly to the existing concrete member. Dimensional and clearance constraints. As noted, particularly for section enlargement, is the owner and the architect okay with encroaching on space that was previously available? Accessibility during the installation process and also during long-term for maintaining and accessing the selected method. Operational constraints, aesthetics, as we previously noted, and lastly, the availability of materials, equipment, and qualified contractors. These are the references that we use to develop and enhance the TechNote. We, again, reference ACI codes, primarily many ACI guidelines, ICRI guidelines, and several authored documents. I thank you for your time. I'll close with one final comment that we revisit these TechNotes every several years. And if anyone has noticed any mistakes, missing methods, or things that we can enhance upon or correct, please let us know, because we're trying to better these documents for everyone's use. Thank you.